Better? Better. Awesome. Perfect. Let's try that one more time. I want to talk to you guys about state. We've all had times where we've been reading code and said, it's hard to follow this code. I have this variable set over here, it's unset over here, it's mutated over here. Or I wonder what would happen if I flipped this variable to something different, something that was unexpected. Maybe if it was a yes instead and it should have been a no, and so on. As we make our applications, it's easy when we start. We only have one thing to juggle. We start out simple. We have one variable set in one place. But as we add on more, we have to think about more things. We have more than just one thing to hold on to, more than just one variable to check over time. It becomes hard to juggle everything, where we can't figure out what variables are set where or which variables matter most. We spend time flipping through headers and documentation just to make sense of what is up and what is down. Let's consider this example here. We want to fetch some bananas from the network. Easy enough, right? We'll have a Boolean to track whether we're loading or not. We have a little API client that we can drop in, and easy enough, we set the loading property to yes before we kick off our network operation. And when it finishes, we've gotten some bananas, and we set our loading back to no. Easy enough, right? Pretty trivial. But our application grows, and we add another request in here. It's tracking and loading for our bushels now this time. So we're fetching bananas, and we're fetching bushels. And we want to track the state of all of this loading as we go through. But we end up with a bit of a race condition here. What if both of these are called? What if both of these are setting loading at the same time, and one finishes before the other? We'll have an issue with loading at some point. It'll be set to something that we don't expect. Easy enough, right? We'll throw another loading Boolean in there, and we'll make sure when our bananas are loading that we only set bananas loading to yes, and when our bushels are loading, we set bushels loading to no. But as we get more and more complex, we add more and more state in. And state is exponential. We have one Boolean, we have two states. We have two Booleans, we have four states. We have yes, 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 no, no, yes, no, no. And it gets hard. It gets hard to track. State. Let's face it. State sucks. State is never simple. Managing state within applications is difficult. I'm here to talk to you about state and help you commiserate with the big S word. I'm Eli Perkins. You can find me most places on the internet as @EliPerkins. Except on Twitter, this gentleman is @EliPerkins, and I'm actually _ Eli Perkins. I work at a company called Venmo on the iOS team. If you want to dance like these guys to call me maybe, come find me afterwards, we can talk. State. Throughout this talk, I want to equip you with some tools and techniques to help you deal with state, going about developing your applications. The first thing I want to talk about are a couple definitions here. Simple versus easy. Well, what is simple? Simple is to fulfill one task, one job, one concept. It means to have focus. It doesn't mean that you can only have one instance, and I'm not talking about the singleton pattern here. I'm just talking about fulfilling one task. What is easy? Easy is close to hand, something that's familiar to you, something that's near to your understandings, near to your skill set, near to your capabilities. Easy is, can I read that? So we have a little bit of an Objective-C here, and it's pretty easy, right? We're looking at our table view, our frame, our size, our height. And for us in this room, this is easy. This is familiar. This is close to hand. But for other developers, this may not be the case. These square brackets all over the place, those are scary. Those are unfamiliar. So let's take a look at something different here. This is Haskell. How many people in this room know what this function does? I only see a few hands here, right? And to us as Objective-C developers, as Swift developers, this syntax is scary. But it's really very simple in the end. It is just the sum of all digits in an array. And here, we have something even crazier. This is Closure. Closure has parentheses all over the place, up and down. And this may be my fault that it's hard to understand because I've squashed it down to a single line or 2 lines. But it's really very trivial. All this does is takes each integer in the collection, increments it by 1, and creates a new collection. But could you follow this? Is this something that's familiar and close to hand? The inverse is also true. Just because something is easy doesn't make it simple. You might have seen something like this before, where you have a helper class, where you can just throw objects into it, add in some state, make it do some extra stuff, and you could say, I only need to call this one method, and it does everything for me. And while that may be easy, it's definitely not simple. I want to challenge you to push your boundaries a bit today. And some of the concepts that we might talk about here may be a little bit unfamiliar. But I hope that it proves some benefit to you, that different paradigms might have something new to offer. If you leave this talk remembering anything I said, I hope it's this. I hope it's that you compare simple versus easy. I want you to go home and try something new. Try Haskell, try Clojure. Try a new programming paradigm like MVVM or functional programming, and see how it challenges your understanding of programming. So let's dive into it. Let's talk about some actual concepts here. We'll cover a few different ones. We'll start off with some talking about immutability and the value of immutability. We'll talk about finding source of truth in your application. We'll talk about value versus reference types, and specifically in Swift, and how they can help reduce state and kind of leverage your data. And we'll talk a little bit about functional paradigms and how functional paradigms can help reduce state. So we've got some ground to cover, so let's get rolling. Let's talk about immutability. I want to start off with this quote from Lee Byron. It says, "Mutable objects collect time and values." This really means that as we intertwine values, as we intertwine time, we have to really make sense of what time or what values are over time. And mutable objects really complicate that a lot. So this year, Apple gave us something really cool, something called Swift. Swift was really cool. With Swift, we got some really great tools to help facilitate immutability. We got let, which lets us create constant values inside of our applications. The compiler will stop us from making mistakes based around the intent of our variables. We see here in this example, we have an array of a couple of bananas, and we have a variable or a constant that captures the count of the bananas. And if we go to mutate this, the compiler stops us. It says, you can't do that. You can't assign to a let value. And that really helps us reason about our code. With compiler level errors and contracts like this, we can begin to make more sense about our code. We can better reason about our code. And not only with trivial things like counts of arrays. But take, for instance, an HTTP client. Networking can be complex inside of applications. And we need to kind of figure out where the truth lies inside of our application when we go to construct these objects. We can begin to create data flow within our applications that helps us derive a source of truth. In this example, in order to create an HTTP client, we need to supply an access token. We can't create an HTTP client without an access token. This is really powerful. We no longer have to wonder whether we've authenticated our HTTP client. We need to have an access token to get there. And our access token can't change out from underneath us. Once we create an HTTP client, that value is constant. We can begin to very much reason about our code and think about our code logically. As you're going through making changes in your application, you may ask this question: what is the impact of the change that I want to make? Rich Hickey said, if you can't reason about the software, you make it harder to make these decisions. Leveraging immutability helps us understand and help us reason about our code. We remove complexity of time and values over time. I propose that designing with immutable data structures in mind, you'll be able to confidently make decisions about data flow in your application with fewer concerns. So let's move on to the next topic. We've kind of started talking about it a little bit so far, but let's dive into it some more. Let's talk about source of truth inside of your applications. As data flows through your application, you must decide where your source of truth lies. As we move from view A to view B to view C to view D, we must decide where our truth comes from. As you add new delegate methods on, we create notifications, and we change some data for our users, and all of a sudden our data doesn't only flow from A to B to C to D, it also flows from A to C, and from C back to B, and D back to B as well. And we complicate things this way. It's hard to find source of truth. Consider the flow of a potential music application where we have an array of artists, and we choose one, and we move on to that artist's albums, and from an album to a song, and diving down into a song. This left to right flow of information helps give us more of a view of what the source of truth is inside of our application. An artist has albums. An album has songs. And you can see the data flows from left to right. In this diagram, we only have one-way arrows. We're not intertwining everything. We're not complicating everything by relating things back to one another. Sure, your song may know what album it's from, but does it need to communicate that up to the album model? One great benefit we get from this as well is the ability to modularize and reason about smaller changes in our data. If we make a single change to our album, will that affect the song as well? Do we need to reload the entire artist list or the album list if an artist changes? We need to ask ourselves these questions as we go about designing our code. As we tackle this problem, we begin to reason about our truth as a function of the state of our view. If the source of truth for our song is the song model, let's make sure we update the view when the song model changes. If we ever need to consider about changes to an album when we're looking at a song view, perhaps we've placed our source of truth in the wrong place. Libraries like React really drive this point home. As we go about trying to find source of truth, we can find it in calling this method setState. And every time we supply this state in, our view gets spit out as a function of our state. Another way to reason about this without a framework like React might be with something like view models. Consider a couple of view models here. We have a song view model, which has a song, and an album view model, which has some song view models and a URL and maybe an image. For those not familiar, view models can help function as a layer between our model and our view. We can then compose the data from multiple sources. You can see here that an album view model has a song. And we can begin to reason a little bit more about the truth in our application and where our data lies. If we were to construct a song list view model where we wanted to show a table view of all of the songs, perhaps we might create a song list view model which has an array of songs. Or a song cell view model, and we want to show the album art in that song cell. Perhaps our song view model should as well have an album view model attached to it to get that image. And we can create a function which grabs that image out for us. As our album's image changes, we don't need to update the views for our song title or our other properties about our song. We only need to consider that the album here is our source of truth. We can better reason about our code and about our data and about the state of our application. Another great benefit we get from this is the ability to modularize different smaller pieces. We can create functions that go from artist view models to artist view model, which has many albums. We can create functions to do this. Model view model, MVVM, is one great way to do this. There are other explorations in this. For example, functional view controllers is another exploration, where you can create state of your application as a series of functions to chain together. It's really important that as you go about designing your applications, you decide where your source of truth lays. So let's dive into some more concrete stuff. Let's talk about value versus reference types in Swift. So Swift gives us some really nice value types. We have not only things like structs and enums, but better reliable value type semantics around strings now, and numbers, and dictionaries, and arrays. We can better reason about these. We've breathed new life into our application and how we pass values around our app. Natasha talked a little bit about this as we kind of dove into value types before. With value types, in juxtapositions to reference types, we get a clear ownership of data inside of our application. In Swift, when we use value types, we don't need to worry about the data as we pass it around our system. we only pass values around. Values become our boundaries. Here we have a banana, which can be peeled or not be peeled. And as we create new bananas, we say if our banana is a peeled banana, we can make a reference to that banana and make sure that one's not peeled. And our original banana stays peeled, where our reference is the only one that's unpeeled. As we pass values around our system, values are our data. They're semantics, they're let values, or they're specific mutating values, define how these objects should be used. This lets us more easily reason about our code without worrying if our bananas will get peeled from out under our noses. One enormous benefit that we get here is not only can we reason about our code, but we can reason about the data inside of our code. Objects are not data. Values are data. Objects have unexpected behaviors, shared state, and mutability. Data is just data. Data is inert. And values are inert. Values are data. Another quote from Rich Hickey again, let data be data. The great Rich Hickey. So I propose to you that using value types inside of your application will help you reduce state, will help you provide a source of data that is reliable due to its mutable structures. There are still places where you may need reference types, where classes may be beneficial, and it's often due to Objective-C interoperability. But values can help reduce state. So let's take a look at a little bit of an example. I grabbed this from the Pistachio README. Pistachio is a JSON parsing library and whatnot, which is used Monocle under the hood. Monocle is for lenses. And it really showcases how value types can really be beneficial. We have here a couple of simple structs. We have a city and a person, origin and a person. And we can create these things called lenses around them. And lenses give us immutable types that we can still work on. We can see here that when we create a person named Felix with the origin city of Berlin, we can also create a Rob here. And we can get the property of Rob's name, and it's Rob. But as we get the property of Felix's name is still Felix, even though we've changed the values from the Felix person into the Rob person. And this is really beneficial. I won't go into the other benefits of lenses or use the word monad to blow your mind. I'll let that for the next talk. But I wanted to show you one way that we can use values and use immutable data sources to find truth inside of our application. At this point, we haven't drifted too far away from what is familiar or close to hand in terms of iOS development and Swift and whatnot. But I want to spend a little bit of time diving into something that's a little bit more unknown. Let's do a little bit of an exploration into some different programming paradigms and compare how they work with data. So let's take a look at a procedural way of talking about a few different objects. Take, for example, this monkey class. We have a monkey who has a stomach, and we can shovel some bananas into this stomach. We can create a monkey and create an eat function, which works on the monkey and appends a banana into his stomach when we call it. And we can introspect into the monkey's stomach and see that there is a banana in there. This is procedurally how we might write something like this. But this has some inherent problems to it. The monkey's stomach is shown to us, so you shouldn't be able to see into a monkey's stomach. And the knowledge of the deep structure of what a monkey is and how it eats. Also, when we call this eat method here, we lose the values of the monkey stomach before and thus mutate the monkey in place itself, losing our benefit of value types. A more object-oriented approach might look something like this, where we have the same monkey, but his stomach is hidden from us now. We have an eat function still, but now it lives on the monkey object itself, and it's still doing that, but we have no knowledge of the outside world has no knowledge of the monkey's internals. It's hidden away from us. This is one of the benefits that we get from object-oriented programming. We hide the internals of the monkey, not having to know what the internals are, and things have gotten a little bit simpler. You can see we create a monkey and we tell the monkey to eat. We pass a banana in and we have a happy monkey. So in our first example, we had mutable data and separate data encode. In this next example, our object-oriented approach, we had mutable data, but we combined our data and code together. They lived closer to each other. So let's look at a functional approach and what a functional approach might look like. You see now we have a struct instead of a class for our monkey. And we can create a function called eat, which takes in a monkey and a banana and creates a new stomach for the monkey and puts the stomach inside the monkey itself and returns that monkey. Well, this may not be the most clear approach, right? It's where we kind of lean towards object-oriented approaches like this. It makes more sense to us in the real world. But this functional approach really fosters immutability. A monkey's stomach is always just a stomach. It never changes over time. It is a value over time. As our monkey's stomach changes, our monkey changes. We start out with a monkey with an empty stomach, and we call the eat function, passing in the monkey, and we pass in a banana as well. And we can see that our two monkeys are not the same. Monkey, what we started out with before, still has an empty stomach, while our fed monkey now has something inside of it. We have two separate values. We have data here. We don't have the complexity of mutability. So let's get a little bit more creative. Say we have a troop of monkeys now. We can then feed the monkeys by mapping over the troop, applying the eat function, passing in the monkey object and a banana. And we notice a few things. We get some fed monkeys out at the end. But our troop at the beginning is still a troop of unfed monkeys. They still have empty stomachs. We haven't changed those monkeys in place. We now just have more data. We've removed complexity of time. We no longer need to worry about how a monkey has changed. Now only that our monkey is now fed and happy. And we can even get a little bit more complex. Let's even feed this troop 2 bananas, right? We can do cool things now. We can find the count of the bananas that are in our fed troop's stomach, and we can find the count of the bananas that are in our super-fed troop's stomach. But notice that as we go about doing this, we never mutate our troop in place. Our data lays the same. So let's compare this back to our other approaches that we had before. We've now gone from having mutable code, mutable data, to having immutable data. But we still have separate data and code. One of the things that we liked about the object-oriented approach is that things make sense to us in a real-world sense. And so there's a concept that Gary Bernhardt has kind of talked about a little bit called FOO, where we can have immutable data, and we can have combined data and code. And FOO brings us back to our object-oriented brother a little bit, while still adapting the functional mentality. So here's what we had for our functional example. We had a monkey, and we had this eat function, and they lived apart. Let's just move that eat function onto a monkey. And at this point, we can kind of reason about our code a little bit more. We have the stomach still, and we can still create that new stomach with the monkey. But this eat method lives closer to our monkey, and we can call it on a monkey itself. And we've regained some of the things that we liked about object-oriented approaches that makes more sense to us in the real world. And this is still functional, even though we call it faux. But at this point now we have immutable data and combined data and code. So I hope I've given you some brain food through all of these topics, and I want to challenge you to try some new ways of thinking and reasoning about your code. And as always, haters gonna hate and staters gonna state. If you want to find out some more information about some of the things I've talked in these talks, you can check out these sources here. This entire talk is up on GitHub too, so you can go ahead and grab those. And I want to say thanks, and what questions do you have for me?